Okay, I'm giving us some practice with finding the determinant of matrices whose elements are sometimes parameters rather than numbers. We really should just treat the parameter as if it's a number. Nothing has changed. So the determinant of this matrix here, Colin got it right. It's -1, because 1 times -1 is -1, minus this cross product here, which is 2 alpha. Right, that's the answer. So now let's apply this. That's easy, right? Is that easy? It's not confusing. How about that? It's not confusing, right? Well, how about this? If anyone's confused by that, let me know. Otherwise, I'll assume it just makes perfect sense. Who cares if this is an alpha and not like a 3? If it were 3, then this would be -1 minus 6. The answer would be -7. Okay, well, we can't say that it's -7, but we can say it's -1 minus 2 alpha. You're going to do the same thing when you get to, I'm going to share, I'm going to go back to sharing this. When you get to this, you're going to have a matrix here of coefficients, alpha. So let me just read out from left to right, first row, second row, third row of the matrix of coefficients here. And just make sure that you guys did the same thing when you did your homework. And tell me if you think I don't understand where I'm getting this, but this will be a matrix that's alpha, beta, 1, 2, -1, 1, 1, 0, 5. That's your matrix, AE. When you get to this question right here, determine what conditions must hold for the system of equations to have a unique solution. All you have to do is take the determinant of that matrix I just said and set it not equal to 0. And then you'll get an expression that's not equal to 0. You could just stop there. You could just stop there and submit that. And I would give you full credit for that. Or if you felt like it, you could simplify it a little bit to say a little bit more about alpha, beta, or delta, but you don't have to. If you just give me the condition that the determinant that matrix is not equal to 0, that's an answer. That's an answer to that question. You guys see that? You don't have to plug in alpha or beta or delta. In fact, you shouldn't plug in any number for a parameter that you don't know the value of the parameter. You just leave it as a parameter. But that's how you answer that question. Okay? Once again, I'll have to just assume that silence is okay.
Yeah, that helped a lot.
Okay. Now let's think of the second thing that's being asked. Solve the system of equations using Cramer's rule. Well, here, actually, you'll take the thing that you just calculated in the first part. That's the determinant of A. That will become the denominator of your expressions for x, y, and z. So you'll find x, y, and z, and each of those will be a fraction. And in the denominator of each fraction will be the determinant of that matrix of A, determinant of A. X, y, and z, they all have the same denominator. Now the numerator has changed. The numerator, according to Cramer's rule, to find the numerator, you take the determinant of the matrix, which is formed by replacing the ith column of A with the vector of constants, the right-hand side vector of constants of this system. So for the first expression, x, you would replace the first column with the vector of d. Well, what is the d vector in this case? Think about it. You need to move things to the right side. So it would be delta. Delta would be the first one. Then 0, because there's no 0 over here. Then 2. So delta 0, 2 will be your matrix. Oh, sorry, your vector that you replace it with. You guys
So
get what I'm saying?
Rule, you just move that vector that we just found, delta 0, 2, and you replace it with the first, second, and third columns and find the determinant of each.
Yeah.
So I guess 3 times.
Yeah.
Okay.
That's what we. So what is x star? X star. I can write it for you right now. It equals. I'm going to use this formulation here. If you just write instead of writing a matrix with braces, if you just write it with a straight line, that's kind of a shortcut for saying the determinant of that matrix. But for that, I don't know if I have enough space here. I gave myself not enough space. But the first column is going to be replaced by delta 0, 2. So that's what would actually go there, right? A delta, a 0, a 2. This is actually supposed to be just a straight line. Then the next column, it's unchanged. It's the real coefficients of y, which is beta, -1, 0. Isn't it? Hopefully you guys did something like this. If not, I don't care. You can do it again and resubmit it. Just email me and I'll like regrade it for you if you want. And then the third column is the coefficients of z, which is 1, 1, 5, isn't it? Is that right?
Yeah,
Yes.
I got that.
Yeah. So just like before, it's okay that there's a parameter here, delta, and there's a beta here instead of a number. Just treat those like numbers, and you can find the determinant of that 3 by 3 matrix. In the 3 by 3 matrix on the bottom, which, instead of this, it's alpha, 2, and 1, but the other ones are the same. Beta, 1, -1, 1, something like that, 0, 5. That's what X is, X star is. I don't want you to just leave it like that. If you did and you already submitted it in your homework, I don't know if I'll penalize you, but that just isn't quite what I would consider to be the answer, because you're just writing it as a determinant of a matrix. It'd be better for you to actually calculate what the determinant is. Of course, there will be a delta and a beta in the top, and there'll be an alpha and a beta in the bottom, but that's okay. That will be your answer for what X is. That's what I mean when you say solve the system. Solving the system of equations means find X, find Y, and find Z. Does that make sense?
Yeah, that helps a lot.
Cool.
Thanks.
And how about this last one, which I think perhaps is the hardest thing I asked you to do. Perhaps the hardest thing I've asked you to do all year is this one, but that's okay. I want to challenge you guys on your homeworks, because that's sometimes the best place for you to take some time to try to figure out what's going on, rather than quizzes or exams or something like that. If alpha equals 1, what must beta and delta be in order for there to be an infinite number of solutions? Well, you're going to look at you know what? There's a shortcut to this that I don't mind telling you right now. Did anyone do this by finding the determinant and then getting that equation and then just kind of searching for ways to make it consistent? Or I'm kind of curious, how did you guys attack this last problem? Does anybody? Sorry.
So the thing I did was I set the determinant of A equal to 0.
Sounds
And then
good.
That's how I got beta. And then I went to the X stars, Y star, and the Z star to see where I could get one of the formulas for the top or the bottom of the fraction equal to 0.
Okay. Without telling us what beta and delta are, did you get an answer for beta and delta?
Yes.
Okay. Yeah, don't tell us what they are, because I don't know. I feel like giving people just a second chance to turn in this homework if they want. But let's talk, instead of giving you the answer, let's talk about how you might get it. And so I think it's Jonathan was just talking. He sort of described a way, which is take this determinant of A, set it equal to 0, right? Instead of setting it not equal to 0, this case, you set it equal to 0, and you can actually calculate what beta is based on that, because alpha is determined. Beta will be the only sort of free parameter, and you can determine beta using that. Then you got to find out what delta is. You can probably go back to what you found out for X star, although I'm not sure that's going to work. At least I can't see how that works exactly.
So the bottom ends up being undefined.
Okay, so you figured out that.
So then that's where I moved on to the Y. To
Okay.
the Y to get the.
You know what? Maybe that works. Maybe it's not. I'll take a look at your homework, Jonathan. And in fact, you may very well have gotten it like exactly right. Perfect way to do it. And I'm proud of you. But let me go with a different way. And that is, it's actually what I wanted to talk about. So this is a good segue to what I wanted to talk about, kind of to summarize some of this material that we went over last class. And that is, what does it mean when the determinant of something equals 0? I kind of want to, let me actually go back to maybe some slides right now. I think it'll be worth talking about. So this is an interesting idea. It's a good point. I want to make it really well. Here's the definition of a determinant. Everybody knows that, hopefully. Slideshow from current slide. Okay. The determinant is just this, cross product AD minus BC, or some higher dimensional version of it, right? Even down here, you can see how it has this property of this product minus this product, EI minus FH. So even if you went a 4x4 matrix, it would still all boil down to this AD minus BC. So I just want to talk about what's happening here when this, let's just look at the 2x2 for now, because the 3x3 and et cetera, it gets too complicated. But the point I'm making right now can be made with a 2x2 matrix. What does it mean if the determinant of a 2x2 matrix is equal to 0? Well, literally, it just means AD minus BC is equal to 0. But what does that mean? If you think about the information that is contained in the matrix, if the determinant is equal to 0, you actually have less information. So there's this term called rank, right? The matrix has a rank of less than 2. And I don't even really want to spend a lot of time telling you what rank means, but it's a term of matrix algebra. It's to describe how much information is being conveyed in the rows or the columns, but let's just say the rows of this matrix. And let's say, this is data, or this is a coefficient. This is some number that you care about, A, B, and C, D. And because it's a matrix, you're going to probably be multiplying it by something. You may be working with this matrix. You may be multiplying it by something. But anyways, what matters is what happens A times something, B times something, and C times that same thing, D times that same thing. And I know this is a long way for me to make this point, but if the determinant is equal to 0, then A times that something, let's call it X and Y, A times X and B times Y is going to be collinear. And therefore, the same relationship of X and Y, perhaps just sort of stretched in some way, but it's still the same relationship of X and Y. A and B is representing a relationship between X and Y. That's the same relationship between C and D. And why? It's because there'll be multiples of each other. It means that one row is simply a multiple of the other row. That's what that means. Let me try to explain. I'm going to annotate, I think, for a bit. I like annotating. Draw. Okay, so here's a matrix A, B. Now instead of the second row being CD, I'm going to make this assumption that it's some multiple of A and of this first row. So I don't know. I think of sometimes K as being a generic integer multiplier. K times, doesn't have to be an integer. I'm going to say it's an integer. KA and KB, something like this, right? So now I'm just talking about a matrix where the first row is AB, the second row is KA, KB. I'm asking now, what happens when you take the determinant of this matrix? When you take the determinant of this matrix, you're going to get A times KB minus KA times B. That equals 0. And now I'm going to argue something even stronger, which is that anytime you get the determinant of a matrix equal to 0, it's because you can write one row as a multiple, as a, what's the word? You multiply each term as a, not a parallel vector, but a linear combination is also an expression that is true, even though I haven't told you what a linear combination is. But I think you get the point. It's like a multiple of the other row. That's what's happening when the determinant is equal to 0. The determinant is equal to 0. It's like I can write one of the rows as a constant multiple of another row. Because if this weren't true, then this determinant wouldn't be equal to 0. But because it is equal to 0, it is true. You guys get this point? I'm just saying that's what's happening when the determinant is equal to 0. You get one row that's a multiple of another. So let's use that fact to go back to the homework and see what kind of insights we might have when looking at this homework. I think I did it. Okay. What must beta and delta be in order for there to be an infinite number of solutions to the system of equations? Well, one of the rows has to be a multiple of the other. There has to be some kind of consistency across the rows that corresponds to, I can take one equation, multiply it by some constant, and get another equation. Or a linear combination of two equations. I didn't say that, but for the 2x2 case, it's simple. But for the 3x3 case, it isn't necessarily that one equation is an exact multiple of another equation. It could be that it's a combination of two equations. But that's what's happening when the determinant is equal to 0. And that says something about this system, what has to be happening here. And it's perhaps a shortcut. If you let alpha equal to 1, what will you see? X plus beta y plus z. That's pretty close to this, but not exactly. I really think this question is difficult, right? Because you're going to have actually a lot of algebra to do just to figure out how one of these equations could be consistent, because it says the same thing. It has the same information about X, Y, and Z. It has the same information as the other equations. That's what we need to look for, that case, the case where, let's take the top one. The top one is just somehow can be derived from the other two equations. That's what we're looking for. Maybe that's a shortcut, maybe it isn't. But if you treat alpha equal to 1, you get X plus beta y plus z minus delta equals 0. That's how can you get that from these other two equations? That's something to think about. How can you get that first equation from the other two equations? I don't know. Does anybody see an easy way to get it? Because for example, if alpha equals 1, you can just sort of forget about it. You have an x here. You also have an x down here. So right there, you can see those are the same coefficients on x. If beta were 0, then it would have the same coefficient as y, but it doesn't have the same coefficient on z. It would be 1 here and 5 here. Okay, the second one is also close, but not the same. It has the same coefficient on z. If beta were -1, it would have the same coefficient on y, but it doesn't have the same coefficient on x. And so what you're looking for is some case where they could have all three, x, y, and z, have the same coefficients. And then you'll be able to say what delta must be equal to, or beta and delta together, what they must be equal to in order to have this consistency across all three equations. That is a tough problem. Maybe think of it like a bonus. You know, if you got it, very good. If not, I'm not gonna hold it too much against you.
Would you ask us a question like that on a quiz or a test?
Probably not, no. But I do want you to see maybe how it could be solved. The problem is find a value for beta and delta such that this equation can be written as a combination of these two. So here's how I would do it if it were me. I would look for Z is the thing where I don't have any way to change it using beta, or actually x2, x and z. So first try to nail down what you need for x and z, and then you have this freedom for beta. You can let beta be whatever you want, at least for now. So first think about x and z. How can you get these two equations to have a coefficient of 1 on x and a coefficient of 1 on z? Do you get what I'm saying? There is a way to do it. And I'm not sure if I should do it for you now or not.
But if we get as far as like D1, D2, and D3, is that pretty good?
Yeah. Did you actually take you took the determinants of those?
Yeah, I honestly just did it. And I was
Yeah.
just making sure. You said that so we can have like delta and beta in the numerators, and then just the denominators can be the same because it's determinant of A.
The
So
denominators will be the same. Yeah.
Yeah.
The numerators will be different for x, y, and z, of course.
Mhm.
But
they'll have but it's okay for them to have letters or parameters.
Yeah. Oh yeah.
Yeah.
In fact,
Okay.
they have to.
Yeah.
They have to have letters because you don't know what beta and delta are.
Okay. I think I was just a little bit confused too because I moved on and I realized that you said if alpha equals 1, so I didn't know if I should go back to the.
Oh no,
determinants and
that's
plug
just for
in.
this. That's just for this last question. You should
Okay.
think of this last question as kind of separate from these other
Okay.
two, and it's much more difficult. So if you didn't get this one, I think that's okay. Don't worry about that. In order to get this, you'd have to find some constant to multiply by this equation and some constant to multiply by this equation, so that when combined, they give you this equation. That's what you would need to do, or one way to do it. I think Jonathan's method may have also worked. That it sounded like it had some promise to it. But anyways, if you feel like doing that and turning it in later for some more credit or something, you can. But once again, you don't have to. You can kind of think of that last one as almost like a bonus. Whatever, I'll treat it that way. Okay, I think we can be done talking about matrices right now. Hopefully, you guys have any other questions, maybe from 1, 2, and 3 that we haven't done that you are curious about? If not, the next thing I wanted to talk about was functions of multiple variables. I think we could do that right now. That's okay. I do have some slides about that, but I put it in what's called partial differentiation. But ultimately, we're going to end up talking about partial differentiation. But before we do that, why is this all blown up like this? I think it's because my computer. I think it's a flaw in Zoom that the menu from Zoom covers up some of the buttons that you would need to press to be functional with your your other programs that you want to be using. That seems like a design flaw to me. Like what I really want to press is slideshow, and it won't let me. Okay, I got it anyway though. So let's just talk about multivariable functions for a bit. And that is really any function that has more than one input, but still produces a single numerical output. That's a function. By the way, a function can't produce more than one output. If it produces more than one output, it's not a function, it's a correspondence. But okay, a function that produces a single numerical output that has more than one input, it's called multivariable. Or sometimes it's multivariate. Instead of BLE, it becomes a T. Okay. Economics is filled with examples of multivariable functions. Maybe the one I want to talk most about right now is called a production function. Most of your econ majors, I believe, right? Is there anyone here taking this class who isn't an economist, isn't taking economics classes? What is a production function? You guys are okay with production functions, right? You've seen production functions before. Clear this. You're all drawings. What is this? What is a production function? You guys know? How would I draw a production function? It's actually hard to draw because it's three-dimensional. It's three-dimensional, but on this axis is labor and on this axis is capital. A production function says, well, for any value of labor, let's say 10 units of labor and 5 units of capital, you get this point here. And the function, the production function, what it tells you is the amount of output that you get, the quantity of output. I should have put f of 10 and 0, by the way. This is wrong. Or f of 5 and 10, sorry. No, 10 and 5. You do the x-axis first. You do the x-axis first. F of 10 and 5, is that right? Now I'm questioning myself because I usually put f of k and l. Should k actually be on the x-axis and y on the right on the? That seems wrong to me too. This is a conundrum. I can't have it both ways. I would like l to be on the x-axis, but I would like k to be the first argument. Can't have it both ways. I'm going to do it. I'm going to put k on this axis just because I want k to be first. Because that's how I'm used to seeing it, f of k and l. So what is a production function? It says, given 10 units of capital and 5 units of labor, I get some quantity of output. Maybe the quantity is, let's say 40. Is this enough to tell you what the production function is? I've given you 1 point on the production function, but I haven't told you what the production function is, right? What is a production function? You should be able to give me any point here, any k and any l, and it'll tell you what capital F is. Remember, capital F is, you're like a business and you're producing widgets, and this F function tells you how many widgets could you produce with this many units of capital and this many units of labor. The answer is 40. Well, actually, if I think of this mathematically as a function that's defined for any k and any l, although usually it's positive or at least non-negative. Let's assume that production functions in this class and probably in every class, the inputs have to be non-negative. You can't have negative capital and negative labor. It might be something like this: f of k l equals. How about? Ooh, I gave myself an odd one, didn't I? I didn't mean to do this. How about this? 4/5 KL. This is a production function here, right? This is 1 point. This is just 1 point on the production function. And if you think about it, it's more than just two-dimensional. It's almost 3-dimensional. Like there's a, if this 40 is equal to quantity, you know, where Q is the quantity of output, then it's almost like there's a third dimension on this. I'm be very hesitant to try to draw a third dimension coming out from the two dimensions that you can see, but there's like a third dimension of quantity that comes out somehow. I don't even know how to draw it. It's too hard. But just letting you know, what we're dealing with now is no longer two-dimensional graphs. They're the type of graphs that it's hard to draw on a piece of paper, because each point, if you draw, let's see, K is an input, L is an input. So you're using up the two dimensions of the paper for your inputs. Where is the next dimension that you would need to draw the output? It would be coming out of the paper. So you already can't draw these things that look like production functions. Okay. What can you draw? You can draw something called a isoquant, which is the set of all points that give you the same. Hey, that's actually a pretty good isoquant, right? This could be the set of all points of K and L that give you the same quantity. And so you can think of it that way, and economists do still try to visualize a function like this. But let's really delve into this guy right here, this production function, and say what's going on with it. There's some properties that I would like us to know just about what happens when you change K but leave L fixed. Right? That's an interesting thing. What happens when you change K capital but leave L fixed, or vice versa? You change L but leave K fixed. Another interesting thing is, what if they're both changing at the same time? What if they're both doubling? Right? I take this same firm. It's at F of K 10 and 5, and now I'm going to say, what happens when K is 20 and L is 10? By the way, what do you guys think happens? What happens to quantity? Does I double capital, I double labor? Does the quantity also double? True or false? Then if I double capital to 20, I double labor to 10, then the quantity will double to 80. Is that correct? True or false? K prime is, you have a 50% chance of getting right. Somebody guess, is it true or false that Q prime will be 80?
It would quadruple, right?
It would quadruple. Thank you, Jordan. It's not 180, it's 160. That's in fact sort of an inherent property of this function, is that if I were to double the inputs, I would quadruple the output. There is a name for that type of function that I want us to know. That type of function is called homogeneous of degree 2. So it's a property of functions called homogeneity that says, if you take a function and you double all of the inputs of the function, it doesn't matter how many inputs there are, if you double them all, if the output is then quadrupled, the name of that type of function is called homogeneous of degree 2. Okay, and in general, this homogeneous of degree, n, where n is some number, n is the exponent that the output is multiplied. The same constant that you multiply the inputs with, n is the exponent of the constant you'd have to multiply the outputs to. So the fact that, here, if I double the inputs to 2K and 2L, it gives me with this 2 squared of the quantity. So I have some slides here. We'll explain homogeneity a little bit better. But a lot of production functions in economics, they have this property. It's a nice property, and it's called homogeneity. Okay, so we're gonna talk about the partial derivatives of a function. And the partial derivatives, I think, can best be explained as what happens when I fix one of the variables of the function and allow the other one to change. That's what I was asking before with, like, if I fix one and I allow the other to change, there's a name for that too. It's called a partial derivative. So the partial derivative of a function tells you something about this sort of unilateral change in one of the inputs. Like if I went from here this way, right? I just allowed K to change, but I fixed L. And I was wondering, okay, how fast does quantity increase? And what's the rate of change of quantity with respect to labor? If I'm fixing, I'm sorry, with respect to capital, if I'm fixing labor and I'm going in this direction. Whereas this would be the partial derivative with respect to L. So man, this is getting too messy. I need to go away from this Zoom, this whiteboard, and go back to my slides because it's just way too messy. Here we go. Once again, it won't allow me to get to it. Thank you. All right, so that's a production function. Utility functions, not going to draw a picture of it, but that's the same idea where you can have multiple inputs. You have different types of consumption, but you only have one output, which is utility. You get what I mean by input and output? I'm talking about the function. The input into the function are how many units of each item that you consume. And the output of the function is how much utility do you receive from it. Okay, here's some mathematical examples of functions of more than one variable. This one, without any context, you can't really tell much about it. F of x and y equals x squared y plus 2y cubed. This is a function. You put in x, you put in y, then I could answer what f is. Sometimes you might actually think of this as equal to a third variable, which is z, right? There is no z here, but it's reasonable to think, okay, this is like saying x squared y plus 2y cubed equals z, where z is simply just the output of this function. Here's a very special type of function, which is called Cobb-Douglas. It's named after these two economists who first wrote about this class of functions when they were estimating production functions of firms. And what their point was, they didn't just pick this arbitrarily. They said, this is an important type of function because we believe that when firms are producing as much as they possibly can produce, given a certain amount of labor, like let's say X is labor and Y is capital, then it grows, it changes according to this formula, where A is some constant, X raised to some power A, Y is some constant, sorry, B is some constant, Y is raised to that power, and alpha is like some multiplier for the whole thing. That seems to describe a lot of firms and how they can produce things. They can produce things according to this Cobb-Douglas. So I think we'll use it a few times in this class just as a standard function to look at, to be honest. Okay. Okay, this is trying to get you to be more familiar, because we'll do it later when we talk about total derivatives, which is coming after this. But you can take any function and create a new function by replacing the arguments inside. So for example, f of xy, if it's this, I could also talk about f of 2x and 2y. That's almost like, it's the same function f, but the inputs have changed. They've now doubled. And what would happen if you did that is simply you'd get a new function here. So if f of xy equals x squared y plus 2y cubed, then I can say what f of 2x and 2y is simply by replacing x with 2x. You would get 2x squared times, instead of y would be 2y, 2 times 2y cubed. But you can kind of see here what's happening with these coefficients is now it's 8x. That y should not be there. I apologize for that. That y should be, that y should not be in the exponents. It should be down there. Yeah, I can fix this with annotation, can I? this should not be there. It should be x squared y. There we go. Fixed. Okay. As of now, all I'm saying is this is something you can do. Something you can do. Does that make sense? I've just replaced x with 2x and y with 2y, and I get this new function. Okay. Oh, by the way, you don't have to just replace, you don't just have to, it's not only possible to replace x with 2x, I could replace x with some function of x, I'll just say some function. I could replace x with some function of t, where t is a new variable. Oftentimes you can think of it as time. So, you see this in economics. F is now a function of x, which is a function of time, and it's a function of y, which is a function of time. X and y could be changing over time. That's okay. And in fact, the way we interpret F is pretty much fundamentally the same. It's just now X and Y are these state variables, quote unquote state variables, because they kind of represent the state of the world right now, even though it may be changing. And F, maybe F is your output, the thing that you care about. The objective function is F. So there's this whole class of models and just economics where you have a dynamic system. What is it, a dynamic system? It's one that changes over time. How often do you see this? What do they look like when you do see them? They have this form to them, but I want you just to be comfortable with it. F of x of t and y of t it's just like f of x and y, only x and y are now variables of t. So what we're going to do in this class is not go deep into the economic modeling that would generate this, but talk about the mathematics of functions that look like this. In particular, the derivatives of these functions. So you should be getting comfortable with how to do differentiation, both partial differentiation and total differentiation on a function like this, f. Okay. Next question. I'm sorry. Okay. If f of xy equals 8xt, capital A x to the a times y to the b, then what is 2x 2y? Simplify this term and compare f of xy to f of 2x 2yb. So first of all, can you help me answer this first question? What is f of 2x 2y? Should I write it on a piece of paper? I can always do that. I had my phone here just in case I wanted to write on some paper. Do you understand the question? I want you to find an expression for.
Yeah, is it just a times 2x? Oh no, I can't see it.
You can't see it? What?
I
Spotlight.
just stopped sharing. Yeah.
Okay. So here, let me write it again for you. Let me first write. Can you see? F of xy equals a to the x lowercase a y b. Now I'm asking you, what is f of 2x? It was 2x and 2y, wasn't it? Can you tell me what belongs here? I think you were answering it, Kai, weren't you?
Yeah.
Okay. Can you see what I'm writing? Should I zoom
Yeah, I
in?
can see.
Okay.
Yeah. Just a times 2xa, and then 2yb.
You mean 2x to the a
Yeah, to the a.
and 2y to the b.
Yeah.
Can we simplify that at all? So that it looks more similar to the top. Let's do that. Remember your rules here of rules of exponents will tell you that you can take this and say a times 2 to the a times x to the a times 2 to the b times That should be a y to the b. Right? You can do this with exponents. You can separate them out. Now I want to get this term here, a x to the a, y to the b. That's the original term, right? But it's multiplied by something. What is it multiplied by? 2 to the a and 2 to the b. In other words, this should be the last round of simplification. 2 to the a plus b times alpha y. Okay, I'm done. You guys see what I did? I took this original, this is called the Cobb-Douglas production function. I took a Cobb-Douglas production function, I doubled x, and I doubled y. And the question was, what I really was asking and wanted to look at was, how does that compare to the original? And the answer is, this expression here and this expression here are exactly the same. They're exactly the same. The only difference is that I also have this multiplier on the outside. So the way to sum up what I'm saying here is that Cobb-Douglas functions are homogeneous. And we need some examples of this, but yeah, we'll see shortly this whole class of homogeneous functions. It says when I increase x and y by some constant, it can be sort of factored out of the original expression with that same constant raised to some power a plus b. So let me just write that here. Cobb-Douglas is homogeneous of degree a plus b. Cobb-Douglas is homogeneous of degree a plus b because of this. Let me show you perhaps some simpler examples of homogeneous functions, and that will make it. Wait, Amina, when did you say that? I don't know. Okay, a long time ago. Yeah, let's look at some simpler examples of homogeneous functions, and that'll maybe make it more obvious. Okay. You've seen the right thing. So here's the answer to what I said before. It was actually 2 to the a plus b power multiplied by the original function f. And I said that's a homogeneous function. Here's like a definition of homogeneity. If I take f and the inputs to the function f are some constant c times x and some constant c times y, if this expression is equal to that same constant c raised to the n power times the original function f, then we say f is homogeneous of degree n. So here are some examples. Here's a very simple example. This is a homogeneous function. You see why this first one is homogeneous? Annotate. Or can I? What would happen if I doubled x and y? What would happen? 2x and 2y. What would I get? Anyone want to say? It's not, if not, okay. 3 times 2x, I'm going to skip that and just write 6x minus 6 times 2y, which is minus 12y. Which, if you noticed, is exactly double the original. This expression here is exactly double this expression here. Therefore, it's a homogeneous equation of degree 1, HD1. Okay? What about this one? Is that homogeneous? And if so, what's the degree? Anybody able to think about that? I think an easy way to do this is always just double the x and double the y. See what you get. 2x quantity squared becomes 4x squared, isn't it? Plus 4y squared. This is exactly 4 times the original. X squared plus y squared is the original. 4x plus 4y squared is we get after doubling the inputs, the two inputs. That means it's homogeneous of what degree? Can anybody tell?
Would it be 2?
Yeah, it's 2. If you come back to this and you're thinking here like c to the n power, oops, that doesn't look very, c to the n power where c is 2, because c is 2 because I've multiplied this and got 2x and 2y. What is n? N is also 2 because 2 to the second power is 4. And this expression here is 4 times this expression here. Okay, that's right. How about this last one? It's maximum. It's a maximization one. You know how to do max problems? I'm not even going to write this. Equals max. Is it homogeneous? It's hard to write. X becomes 2x. And a 3y becomes 6y. This is kind of an interesting problem because I want to compare the maximum of x and 3y to the maximum of 2x and 6y. And what is the relationship there? Is one bigger than the other? And if so, by how much? You guys think? This is a test to see if you know what I mean by homogeneity. Okay, I only have 10 minutes. You guys understand? Compare this number. Compare the maximum of 2x and 6y to the maximum of x and 3y. What is the relationship between those two numbers? Is it like this, where it's homogeneous of degree 1? Is it like this, where it's homogeneous of degree 2? Is it neither?
Is it just 1? Because it's
You think it's HD1? Why?
because
Because it's
to the degree
because it's double.
1. Yeah.
Is that because it's double? You're saying whatever this is here, it should be double this. Is that Kai who's talking? I can recognize your voice. She's right. Whatever you get here, the maximum of 2x and 6y, is going to be double the maximum of x and 3y, isn't it? I mean, if x is bigger than 3y, then this will be x and this will be 2x. It's double. If 3y is bigger than x, then this will be 3y, this will be 6y. It's still double. Either way, it's doubled. That's what it means to be homogeneous of degree 1. It means when I doubled all of the inputs, the output is doubled. So a maximization function or a minimization function, both of those types of functions are homogeneous. Well, I should say, of course it depends. Of course it depends on what is the maximization of. But in this example, which is kind of a simple example, it is HD1. Okay. I think on the next slide I have like a ton of examples. Oh no, I don't. That's this one. And of course it's a huge mess with all the annotations. Okay. I think some of you already have seen this. If you've had economics classes, especially micro classes already, you will have seen this, but there's a very related concept to homogeneity, and that is returns to scale. A return to scale for a production function is just as a reminder, if I'm going to multiply the inputs by some factor C, and the outputs are greater than C times the original output, that's called increasing returns to scale. You should think of that as a business where the larger and larger you get, the better and better you get, per unit of input at producing the output. It's one where it's like you're able to find new ways of utilizing your capital and labor the bigger you get, and you can produce even more as you grow. That's called increasing returns to scale. Constant returns to scale is when you get exactly C here, right? Now, if I if I multiply my capital by C and multiply my labor by C, I'm equal to multiplying my output by C. That's called constant returns to scale. And then the last one is decreasing returns to scale. If I don't quite get a return, if I double my inputs I don't quite get double my outputs. That's called decreasing returns to scale. And there's this relationship between homogeneity and returns to scale that is described here. If n is greater than 1, the function has increasing returns to scale. Equal to 1 is constant, and less than 1 is decreasing, right? That was true for these back here too. This function, you could say, has constant returns to scale. This one is increasing, and this one is constant. So a lot of this is just reviewing microeconomics, but it's looking forward to doing some calculus on these types of functions. So I certainly don't want to I don't have that much time anyway, 5 minutes. I don't want to do all of these, but I don't know why I gave so many examples. It's like too many examples here. But if you want to look at some of these and say, are they homogeneous? What degree? Do they have constant increasing or decreasing returns to scale? You guys want to take a stab at any of these? This one should be easy, right? If I double capital, double labor, what's happened to output? It has also doubled. Thought that was easy. Maybe it wasn't. It would be 4K plus 10L. That's double 2K plus 5L. So that's homogeneous of degree 1, which is also the same as constant returns to scale. Right? I'm going to assume if you say nothing, then you understand what I'm saying. This function is homogeneous of degree 1 and therefore has constant returns to scale. This one, somebody tell me what it would be. HD, what? Oh, no one's there. Lost you all.
Would it be like 10?
Yeah, what's the value of n? HDN. Yeah, tell me what n is. What number should I put here?
But 10.
10? Oh, no.
Oh, I'm confused by the.
Yeah, sure. Okay, that's fine. I can help. Oh, because you thought this multiply here was 10. If I were to double K and double L, what would happen to this expression? Would it get 10 times, would it get 2 to the 10 times bigger? That's what would need to be, that would need to happen if it was HD10. Just to let you know, if something were HD10, that means if I were to double K and double L, the whole thing would get larger by a factor of 1024, because that's 2 to the 10th power. I happen to know what 2 to the 10th power is. So actually, I mean, thank you for guessing. Actually, I really appreciate you saying something. But it's not HD10. It's HD2, which is increasing returns to scale. You see why it's HT2? If I double capital, double labor, that would be 2 times K times 2 times L. That's 4 times K times L. So the whole thing would get bigger by a factor of 4.
Oh, okay.
So if you doubled K and you doubled L, the whole thing would get bigger by a factor of 4. That's why it's HT2. Okay?
I get that. Okay.
Yeah. This one's just like the one we did before, HT1. How about this one? This one's a little interesting. Homogeneous of some degree that's not an integer. What do you think? I told you this before with Cobb-Douglas functions. Remember what I wrote on the piece of paper? When you see, this is a form of a Cobb-Douglas function, K to some power, L to some power. It's allowed to have a constant here. Here the constant is just 1. But all Cobb-Douglas functions are homogeneous of degree equal to the sum of the two exponents. So it's homogeneous of degree 4/3, strangely enough. And now you tell me, is that constant increasing or decreasing returns to scale? Remember you had this nifty,
The decreasing?
what'd you say?
Decreasing?
Decreasing? I can see why you would think that, but it's not. Were you thinking that because of the exponents being less than 1 here?
Yeah.
That's a reasonable thing for you to think, but it's actually not true. It's increasing.
Okay.
I can try to explain why without taking too much time since we're pretty much out of time. So this will be the last thing I do. This is a function where, let me explain in terms of economics. This is an economics review. There is a diminishing return to each input. Each input, capital and labor, has the law of diminishing returns says, if, the more capital I add to it, the less the marginal product of capital is. The more labor I add, the less the marginal product of labor. That is true for this production function. Because the exponents are less than 1, that means I'll get less and less out of capital. It's like if I had 1 million cooks but only 1 kitchen, I'm not getting a lot out of those cooks. Or if I had 1 million kitchens but only 1 cook, I'm not getting a lot of all those kitchens. That's the law of diminishing returns. However, when you put capital and labor together, they actually do a lot for you in this. They grow by a factor of, or by 4/3. Which is greater than 1, because when capital and labor together have this homogeneity factor of 4/3, it actually has increasing returns to scale. So what your intuition was that, well, this 2/3 is less than 1, that's decreasing. That's only true if I were to increase capital or labor by itself. You would be right. But returns to scale is about when I increase capital and labor simultaneously. When capital and labor simultaneously grow, that's like 1 million cooks and 1 million kitchens. Now that's good, right? You can produce a heck of a lot of stuff there, and that's increasing returns to scale. Okay, I think let's stop there. I think the real meat of what I want to be teaching you about this stuff is the calculus. I haven't even got to the calculus yet, but once we do that, we'll be taking the derivatives of these functions with respect to K, or the derivative of this function with respect to L. And that'll tell you something meaningful in economic terms. And so I'll give you some homework on that. That's due probably, in a week or something, maybe a week and a half before the midterm. But, I want to have this next homework due before the midterm. And when is our next quiz? I think our quiz is a week from today. Quiz is a week from today. In class, we'll talk about, the quiz will be over both some matrix stuff and some properties of multivariable functions like homogeneity, and also partial differentiation, which we need to talk about between then and now. You guys have any questions about that? And remember, if you want to if you want to submit some kind of additional homework stuff to me, that you can. If you want to just go with what you already sent me, don't worry. I mean, you can do that too. And sort of treat that last question as like a bonus. I do think it was pretty hard. It would have taken a long time for me just to do it with you in class today, and I didn't. So, you guys have any other questions? I'm over my time. I gotta wrap it up.
No, that was fine.
What?
I said no, I don't have any questions.
Okay, great.
Okay,
So
thank you.
I'll let you know when that when that homework is up, and you can start taking a look at the next homework when it's
All right.
available. Okay. Have a good day.